Hi everyone, welcome to Go Classes. So in the last lecture, we were discussing countability. We have already seen what is countable set, what is uncountable set. We have also seen the Cantor's diagonalization proof. Yes or no? So in the countability, so far what we have seen? So far we have seen what is cardinality definition. Also we have seen countable set definition, uncountable set definition. We have also seen Cantor's diagonalization proof. Okay, so these are the things that we have seen. Please tell me, are you comfortable with Cantor's diagonalization proof? And did you find this interesting? Whenever we want to prove that some set is uncountable, we can use Cantor's diagonalization proof. And this is very interesting proof. If you apply this, you will find this very interesting. So now let's move on. So we have seen the definition of cardinality. We have already seen that when can I say two set have same cardinality? Set A cardinality is equal to cardinality of set B. When can I say? If and only if there exists a bijection between these. Yes or no? And also remember, if there exists an injective function from A to B, if there is an injective function from A to B, then I can say cardinality of A is less than equal to cardinality of B. Yes or no? So this is the definition of cardinality we have already seen. Okay, so these definitions, all these small results we have already seen. Okay, so you can easily notice all these results. We have already seen all these things. The definition of countable set also we have seen. You can see, when can I say a set is countable? A set is countable if and only if it is either finite or it has same cardinality as positive integers. Yes or no? So I can say the definition of countable, that simply means either it is finite or it has same cardinality, okay, as set of positive integers. We have already seen the set of real numbers is uncountable. The proof we have already seen. Proof using diagonalization. Yes or no? Okay. The set of real numbers, this is uncountable, means there is basically, first of all, there is this set of real number. This is infinite set. Also, we have proved that there is no bijection with a set of positive integers. Yes or no? Natural numbers, comma real number. Natural numbers, comma real number. Between these two, there is no bijection. There is no one-to-one correspondence. This we have proved using Cantor's diagonalization proof. Yes or no? Okay. So this we have already seen. Now let's move on. So these are the definitions you can see. A set is called countably infinite. When can I say a set is countably infinite? Tell me. When can I say a set is countably infinite? A set is countably infinite if and only if you can put it in one-to-one correspondence with natural numbers. Yes or no? It can be put in one-to-one correspondence with the natural number. When can I say a set is countable? If it is either finite or countably infinite. Yes or no? Also, a set which is not countable, that is uncountable. Okay, so remember the definition of countable. When can I say this? Please understand the definition of countable and the definition of countably infinite. Countably infinite. So what is the definition of countable? The definition of countable is like this. Set S is countable. Okay, set S is countable. When can I say set S is countable? Please tell me. Countable means either it is finite or it is countably infinite. A set S is countable if and only if, tell me, what is the definition? If and only if there is injective function from S to natural numbers, or I can say cardinality of S that is less than equal to cardinality of N. And when can I say a set is countably infinite? I can say set S is countably infinite. Is countably infinite. When can I say countably infinite? If and only if set S cardinality is exactly equal to set of natural numbers, means there exists a bijection. Yes or no? Okay. So remember, this means there exists a bijection. This means there exists a bijection. Bijection between S comma N. There exists a bijection between S comma N. And remember what this means. Tell me what this means. This means there exists a injection. Injective function. Okay. There exists a injection. From where to where? From S to N. From S to N. Okay. So if you can create an injection, then you can say that this set S is countable. Okay. This is the definition of countable. Remember, countable means set S cardinality is less than equal to set N cardinality. And when can I say countably infinite? Countably infinite means set S cardinality is equal to set N cardinality. Okay, so this is the definition of countable and countably infinite. Also remember, this countable infinite, this is the lowest level of infinity, right? Yes or no? This countable infinite, this is the lowest level. This is the lowest level of infinity. This is the lowest level of infinity. Okay, this is the lowest level of infinity. Is this clear? So this countably infinite, this is the lowest level of infinity. On this countably infinite, you have like set of natural numbers, set of integers, set of even natural number, even integers, like this. Okay, and so on. So these things you have on this level. Okay. So I hope you understood. And what is countable set? That you already know. Either countable set, this countable set, either it is finite set, either it is finite set, or it is countably infinite set, or it is countably infinite set. Now remember one point, that this countable infinite, this is the lowest level of infinity. Lowest level of infinity. So tell me, this type of set, does it exist? Is there a set S? This is simple question I'm asking. Is there a set S? Is there an infinite set S? Is there a infinite set S such that S cardinality is strictly less than N cardinality? Tell me, is there any such set? Tell me. Let me know. Is there any such set? The answer is no. Why? What is the reason? The answer is no. Because remember, this N, this is countably infinite, right? Yes or no? This N, this is countably infinite. This N is countably infinite, correct? Okay, so you can see this N is countably infinite, and this countably infinite, this is the lowest level of infinity. This is the lowest level of infinity. This is the lowest level of infinity. Okay, yes or no? So it's simply because this is the lowest level of infinity. So is there any infinite set? Is there any infinite set which has strictly less cardinality than N? The answer is no. The answer is no. Yes or no? Is this clear? Please tell me. Let me know. Now tell me another question. Another question I want to ask. Is there a set? If I simply ask you this, now tell me. Now tell me. Is there a set whose cardinality is strictly less than cardinality of N? Is there a set whose cardinality is strictly less than cardinality of N? What is the answer for this question? The answer is yes. This type of set will be called finite set. Yes or no? This will be called finite set. You can take any finite set. You can take any finite set you can take. Okay, so I can basically say the definition of finite set. See, S is finite. When can I say S is finite? S is finite if and only if. When can I say a set S is finite? Tell me. When can I say a set S is finite? If and only if cardinality of S is strictly less than cardinality of N. Okay, cardinality of S, that is strictly less than cardinality of N. Yes or no? So this is the definition of finite set. S is finite if and only if cardinality of S, that is strictly less than cardinality of N. Okay, tell me one more thing. What this means? What this means? Tell me. What this means? This means there exists an injection from S to N, but there is no bijection. Yes or no? What this means? This means injection exists. Okay, this means there exists an injection. Correct? Yes or no? It means there exists an injection from S to N. From S to N. Okay, but there is no bijection. But there is no bijection. But no bijection between S comma N. Is this clear? Please tell me. This is what it means, right? Yes or no? We already know. When can I say set A cardinality is less than set B cardinality? What this means? What this means? This if and only if, what will happen? There exists an injective function. Remember, there exists an injective function. There exists an injective function from A to B. From A to B, there exists an injective function, but there is no bijection. But there is no bijection between A comma B, or I can say from A to B. from A to B or between A comma B. Yes or no? So this is what it means. I hope you understood. Correct? Okay. Now let's move on. So you can see. Now tell me this question. Is there an infinite set S whose cardinality is like this? Now tell me. Is there an infinite set S whose cardinality is like this? Now tell me what the answer? The answer is yes. This type of set is called countable infinite. Yes or no? Okay, this type of set is called countable infinite. So here you can notice, for example, S can be n itself. S can be n itself, integers, and so on. So I can say, this is the definition of countable infinite. This is the definition of countable infinite. S is countable infinite. This is the definition of countable infinite. Agree? Yes or no? This is the countable infinite. Because this is already infinite. So this is actually countable infinite. Okay, so I can say S is countably infinite. If and only if. Tell me. See. So here actually this S will become countably infinite. Okay, here if this happens means S is infinite. Okay, see, if S is infinite, see this will happen. If S is infinite and S, there is an injective function from S to N, then what will happen? Then S will be countably infinite. Then S will be countably infinite. Okay, yes or no? Then S will be countably infinite. Agree? So this is the point. Okay, so remember, if this happens, see, this is the point. If, okay, means I can say if this happens, if there is an infinite set such that there is an injective function from S to N, okay, then what will happen? Then what will happen? Tell me. In this situation, I can say then S has same cardinality as N. Then they have same cardinality. Okay, then they will have same cardinality because this is infinite. Also, there is injection from S to N. There is injective function from S to N. So in this situation, I can say they have same cardinality. Okay. And that simply means S is countably infinite. S is countably infinite. Okay. So all these things, are they clear? Please tell me. So we have already seen all these things. What is the definition of uncountable set? Uncountable means not countable. Yes or no? The definition of uncountable, that means not countable. A set is called uncountable if it is infinite and there is no bijection with n. There is no bijection with set of natural numbers. There exists no bijection between n comma infinite set A. So if you have an infinite set which does not have any bijection with n, then this type of set will be called uncountable set. This is the definition of uncountable set. See, if S is infinite, okay, if S is infinite and there is no bijection between S comma N, then S will be called uncountable. So all these definitions we have already seen. Now let's move on to our next topic. That is 3 equivalent definitions of countable set. Okay, now we will see 3 equivalent definitions. 3 different definitions we will see. 3 equivalent definitions of countable sets. Okay. So far we have seen one definition, right? Yes or no? So far we have seen one definition. Now we will see 3 equivalent definitions. All these definitions are equivalent. You can use any of them. But let me tell you, the definition number 3, that is most easy. Okay. So what we are going to do now? Now we will see 3 definitions, equivalent definitions. You can use any of them. So we have 3 equivalent definitions for countable set. The definition 1 we have already seen. Okay, that is a formal definition, but that is hard to apply. What was definition 1? Please tell me. For countable set, what was definition 1? For countable set, what was definition 1? Countable set is either finite or there is a bijection with natural numbers. Yes or no? Okay, yes or no? Countable set, definition 1. What was definition 1? Definition 1 was that either it is finite or there exists a bijection with natural numbers. Okay, so remember this definition 1, this was formal definition, but this was very hard to apply on the questions. Okay, next we will see definition number 2. That is similar to definition number 1, but that is easier to apply. And then we will see definition number 3. That is easiest to apply. And this definition number 3, this will become your favorite. In the GATE exam, in any exam, you will apply this definition number 3. Okay. So let's see. Let's move on. So let's start with definition number 1. You have already seen the definition number 1. This is the definition. When can I say a set is countable? Tell me. A set is countable if it is either finite or there exists a bijection. Or there exists a bijection with natural numbers. Yes or no? So this is the definition of cardinality. This is the definition of countable. So I can say countable definition 1. What was that? Tell me. Definition 1. This is your definition 1. Countable set. When can I say a set is countable? Tell me. Countable set. This is the definition 1. Countable set is, remember, either it is finite. Okay, either it is finite. I can say either if it is finite, then it is countable. Either it is finite or it is countably infinite. Okay, so I can say either it is finite, means cardinality is less than cardinality of n, or it is countably infinite, Okay, countably infinite. What that means? That means set S cardinality is equal to set n cardinality. Okay, so this is the definition. This is the definition of countable set. I can say countable set means, this simply means S is countable. S is countable if and only if cardinality of S is less than equal to cardinality of n. Okay, this is the definition. You already know. Okay, so you can see either it is finite or there exists a bijection with set of natural numbers. Yes or no? So this is the definition of countable set. I can say either it is finite, or there exists a bijection, with natural numbers. Okay, so this is the idea. Now let's move on. So we have already seen this definition. Now let's see this question. Using this definition, let's prove that set of all finite binary strings, set of all finite length binary strings is countable. Let's prove this. That set of all finite length binary strings is countable. Okay, this is what we want to prove. Do you remember in the last class we have proved that set of all infinite binary sequences is uncountable in the previous lecture? Do you remember? Yes or no? In previous lecture we have seen this set was there, set of all infinite length binary sequences, set of all infinite length binary strings. Yes or no? Infinite length binary strings. Agree? This was uncountable binary strings. Okay, set of all infinite length binary strings. This set was uncountable. Do you remember we have proved it? Okay, so we proved using what? Tell me. We proved using diagonalization proof. Yes or no? We proved using diagonalization proof. So this we have already seen, that set of all infinite length binary strings, that is uncountable. This we have already seen. Okay, and we have proved using Cantor's diagonalization proof. Now let's see in this question what the question is asking. You can see the question is asking if sigma is a finite set, then set of all strings, set of all finite length strings, that is countable. Means this is what we need to prove. See, this is what we need to prove. Notice, show that set of all finite length binary strings, set of all finite length binary strings, that is countable. So here you can see if your sigma is 0, 1, then tell me what is this set? Tell me what is this set? Let me know. What is this set? Set of all finite length binary strings. This is your sigma star, right? Yes or no? This is your sigma star. If sigma is 0, 1, this is your sigma star. You know what is sigma star? Sigma star is set of all strings. Set of all finite length strings. Yes or no? Because in our theory of computation, I can say every string has finite length. In this sigma star, every string has finite length. So set of all binary strings. Okay, so we need to prove that this sigma star is countable. This is what we need to prove. What we need to prove? We need to prove that this sigma star is countable. Sigma star is countable. Okay, did you understand the question? Please tell me. If sigma is 0, 1, then what is set of all finite length binary strings? Finite length binary string, that is sigma star. You already know. In this sigma star, every string has finite length. Yes or no? In this sigma star, you have strings. Every string has finite length. These strings you have, and every string will have what? That will have finite length. That you already know. Okay. In the basic theory of computation course, by default, string means finite length strings. In our sigma star, we have all the strings. Sigma star is set of all strings. And all these strings, all these strings which are in the sigma star, these are finite length strings. This we already know. Okay. So we need to prove that sigma star is countable. Okay. If you want to prove sigma star is countable, then tell me, how will you do it? Please tell me. How will you do it? Let me know. Sigma is 0, 1. This is sigma. And sigma star, that you already know. Sigma star, that is set of all finite length binary strings. Okay. So tell me, we need to prove that sigma star is countable. We need to prove that sigma star is countable. So tell me, how will you prove this? How will you prove this? This sigma star. So you already know this is infinite, right? Yes or no? This set is infinite, correct? This is an infinite set. Okay. So all you have to do, just create a bijection with n. Yes or no? All you have to do, just create bijection with n. So if you want to prove sigma star is countable, this sigma star is countable. If you want to prove that sigma star is countable, to prove sigma star is countable, what you will do? What is the method? What is the idea? The idea is simple. Create bijection with n. Create bijection. Create a bijection with set of natural numbers. Yes or no? Just create a bijection with set of natural number. Now tell me, how will you create? How will you create bijection with set of natural number? Any idea? Give me a bijection between sigma star and set of natural numbers. These are set of natural numbers. Okay, and so on. So tell me. Let me know. Give me a bijection. This is your sigma star. Any idea? Anyone? How to create bijection? Any idea? Let me know. Any idea? For example, if you are thinking, are you thinking that, okay, I will map everyone to their decimal value? I will map everyone to decimal value. Give me a bijection. Give me a rule. Give me a rule. Please give me a rule from sigma star to n. Give me a rule. For example, what should be f of w? What should be f of w? Let me know. Give me a rule. What should be f of w? Give me a bijection. Okay, I want bijection. I want bijection. So give me f of w. I want bijection. So tell me, any idea? For example, are you thinking that this will work, that every number I will map to their decimal value? Okay, will this work, that fw is decimal value of w? Will this work? Will this work? Fw is decimal value of w. Will it work? Will it work? Let me know. This will not work. Why? Tell me why this is not working. Let me know why this is not working. Let me know. If I do this, why this is not working? Because this is not injective. Yes or no? This is not injective. This is not injective. This is not injective because 0. See, first of all, this is not injective. Also, this is not surjective. Also, this is not even a function. This is not even a function. You can notice this 0. Just notice where this 0, 1 will go. It will also go here. It will also go here. Also, this is not even a function. This is not even a function because where it will go? Where this will go? Yes or no? Where this will go? So this is not even a function. Agree? Please tell me. Is this clear? Let me know. So this is not even a function. Not even a function. So give me some other idea. Okay, let me give you the idea. Okay, just notice what I'm going to do. See, there is a problem. This type of problem I need to take care, right? For example, 1, 0, 1, 0, 0, 1. They have the same decimal value, right? Yes or no? Did you notice? And so on. They have same decimal value. Please tell me yes. They have same decimal value. They have same decimal value. Okay. Why they have same decimal value? Why they have same decimal value? Because these extra zeros you can put. For example, this number. For example, tell me, this number is same as this number, right? Yes or no? Yes or no? These two numbers are same. You know, this is also 56. This is also 56. So extra zeros you can put. Now, what the idea? See, clever idea. Now, what the idea? If I want to suggest some idea so that we can handle this problem, tell me how to handle this problem. If you want to handle this problem, just put 1 before it. See, okay, just do this. 1W. Just put 1 before. For example, if you put 1, now they will become different. Yes or no? Now they will have different decimal value. Agree with me? Please tell me. See, if I put 1 before them, okay, then can I say now they have different decimal value? Yes or no? Now they have different decimal values. Please tell me, did you understand this idea? Let me know. A very simple idea. Now they have different decimal values. Agree or not? Please tell me. Okay. Yes or no? Now they have different decimal values. Also, you can notice previously this does not have any image. See, this, all these things, they have no. See, their decimal value is not natural. Yes or no? You can notice their decimal value is not in n. Correct? Their decimal value is not in n. Okay. Now, again, the same idea will work. Okay, the same idea will work. This same idea means if I put 1W, now tell me, will this idea work? Again, this will work. Again, this will work. Again, this idea works. Again, this idea will work. For example, you can notice 1 epsilon. What is that? What will be the decimal value? Please tell me. What will be the decimal value of 1 epsilon? That is 1 itself. That is 1 itself. What is the decimal value of 1 0? What is the decimal value? Please tell me. That will become 2. Okay. What is the decimal value of 100? What is the decimal value of 100? That will be 4. Can you notice this idea is working? Okay. So this clever idea, you can see this is the clever idea. Please notice what I'm doing. I am creating a function from sigma star to set of natural number. Okay. And I'm doing this. F of W is equal to decimal value of 1W. Decimal value of 1W. Decimal value of 1W. That's it. That's it. Yes or no? Now, can you notice this function? This is a bijection. You can just easily check this function is bijection. You can check. Tell me what is the image of epsilon? That will be 1. What is the image of 0? That will be 2. What is the image of 1? That will be 3. Because I am putting 1W. Before everyone, I am putting 1W. Decimal value of 1W. Before everyone, I am putting 1W. Before everyone, I am putting 1W. This image will be 4. This image will be 5. This image will be 6. Then the next image will be 7. Please tell me, did you find this interesting or not? Clever idea, yes or no? Please tell me, did you understand? Let me know. Now you can notice. Now you can notice, for example, this will go to 8. And so on. Okay, just put 1 before it. Did you understand? Please tell me. Let me know, did you understand? See, this is the idea, sigma star. Here you have sigma star. This is your sigma star. Sigma star is set of all binary strings. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, okay, 0, 0, 1, 0, 1, 0, and so on. This is your sigma star. And this is your set of natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. This is the set of natural numbers. Okay. So what mapping I am doing? Tell me which mapping I am giving. Which mapping? I am giving this mapping. I am creating a function from sigma star to set of natural number. And in this function, what I am doing? In this function, f of w is equal to what that? That is decimal value of 1w. That is decimal value of 1w. Of 1w. That is the decimal value of 1w, remember. Okay. Now, can you notice this function f, this is bijection. This function f is bijection. Okay. You can see the image of epsilon, that will be 1 epsilon, means that is 1. The image of this will be 2. The image of this will be 3. Image of this will be 4. Image 5. Image 6. Image 7. Image 8. Image 9. Image 10. Can you notice? Beautiful bijection we got. Just a clever idea that you just put 1. Okay. Means for every w, the image will be decimal value of 1w. This is your bijection. So bijection exists, right? Yes or no? So I can say, so bijection exists. We have created bijection. Bijection exists between sigma star and natural numbers. Yes or no? Bijection exists between sigma star and natural numbers. So tell me what I can say. Tell me what I can say. I can say size of sigma star is same as size of n. Their cardinality is same. And what that means? That means sigma star is countably infinite. Sigma star, that is countably infinite. Or in simple words, I can say, because it is countably infinite, so this is countable also. So this is countable also. So this sigma star is countable set. Understood? Please tell me, did you understand this? So will you remember this idea, this simple idea? Yes or no? This clever, simple idea. Okay. So quite simple. Like this you can prove. So this is your proof. Now let's see the next question. So before that, before seeing the next question, let me tell you. So this was your definition number 1. We have already done practice of definition number 1, right? Yes or no? We have already done practice. Countable set definition number 1. But this was formal definition. This definition was formal definition. It is hard to apply because finding bijection is not an easy task. Do you agree with me? See, some of you might be thinking, sir, from where you got this idea? Is there anyone who is thinking like this? Is there anyone who is thinking, sir, from where you got this idea? I cannot get this idea. In the GATE exam, I will not get this idea. Yes or no? See, some of you might be thinking, sir, you got this idea, but in the GATE exam, I will not get this idea. So don't worry. We will not apply this definition in the GATE exam. This is what I'm saying. This is what I'm saying. This definition, this bijection definition, we will not apply in the GATE exam. This definition is hard to apply. This definition, this is hard to apply. Okay, because this is not easy task. Okay, finding bijection between two set, that is not easy task. So remember, this definition we will not apply for questions in future. Okay, this definition is easy to understand. See, easy to understand, but this is not easy to apply. This definition is easy to understand, but not easy to apply. Okay, if some questions come which are based on this definition, you can answer. Okay, so we will not apply this definition in future. Let's move on. So now let me give you the another definition. Is this clear? This definition we will not apply in the future. In the GATE exam, in any question, you don't have to apply this definition. I will give you much easier definition. Okay, so let's see the definition number 2. Now we will see definition number 2, which is similar to definition number 1, but that is easier to apply on the questions. Okay, that is comparatively easier to apply on the questions. And this is very similar to definition number 1. Okay, actually from definition number 1, definition number 2 is coming. Okay, we will see. We will see from definition number 1, definition number 2 is coming. But this is much easier to apply. So let's see this definition. Definition number 2 of countable set. This definition is like this. Please tell me one thing. From the definition number 1, what you can notice? See, from the definition number 1, what you can notice? Let me know. From the definition number 1 of countable set. In the definition number 1 of countable set, Can I say countables? Every finite set is countable? Yes or no? Every finite set is countable. Finite set S is countable. Finite set S is countable, right? Okay. Now you can notice, if I give you a finite set, can you put the elements in a sequence? If I give you a finite sets, okay, finite set, you can see, if I give you a finite set, now tell me, can you put the elements in a sequence? This is, see, from the definition number 1, we already know that finite set is countable. If I give you a finite set, let's assume this is a finite set. Now, can you put these elements in a sequence? Can you put these elements in a sequence? Yes, we can create a sequence. Create a sequence. Create a sequence. Can you put these elements in a sequence? Yes, I can put these elements in a sequence like this. Okay, I can put A1, then I can put A2, then I can put A3, and so on. Okay, you can see on the first position, this is the, I can say this is the first position of the sequence, right? Agree? This is the first position of the sequence. This is the second position of the sequence. This is the second position of the sequence. And this is the nth position of the sequence, right? Correct? This is the nth position of sequence. So did we cover every element of S? In this sequence, did we cover every element of S? Yes, we have covered every element of S, because anyway, this is finite set. Anyway, this is a finite set. Okay, so you can see like this, you can create a sequence. Is this clear? Very simple. Okay, so we can create a sequence. Now let's see another. You tell me one thing. Other than finite set, from the definition 1, you already know what is countably infinite. Just tell me this point. Countably infinite, let me know. Countably infinite, let me know. Can I say countably infinite has one-to-one correspondence with set of natural number? Can I say countably infinite set? See, this is, let's assume you have this set. Let's assume you have this set S is equal to A1, A2, A3, and so on. Okay, because this is countably infinite, so there exists a one-to-one correspondence with set of natural number. Okay, because this is countably infinite, so I can say this S. In this S, you have A1, A2, A3, A4, and so on. This is your set of natural number. There is a one-to-one correspondence. You agree with me? Because this is countable infinite. Because this set is countably infinite, so there exists a one-to-one correspondence. Okay, with the set of natural number. There exists a one-to-one correspondence with set of natural number. These are the natural number 1, 2, 3, 4. Okay, and so on. So you can see this is what we have. And can you again notice? Can I say this is the fourth position? Just tell me, can I say this is the fourth position? Can I say this is the fourth position? That A4 is on the fourth position because this is mapping with 4. Okay, can I say this is the first position? Can I say this is the first position? Yes, this is the first position, right? Yes or no? Because there exists a bijection, you already know. So finally, you tell me now. So can I say again you got a sequence? Again, this is a sequence, right? Again, you got a sequence or not? You got a sequence or not? Again, you got a sequence. So this is the definition. Now I am telling you the definition number 2. Now I am telling you the definition number 2. And this definition is like this. When can I say a set is countable? When can I say a set is countable? A set is countable if and only if you can put the elements in a sequence. Countable set. Remember, S is countable. When can I say S is countable? Please understand. S is countable if and only if you can put the elements of S in a sequence. We can put elements of S in a sequence. Elements of S in a sequence. In a sequence. Okay. So please understand, S is countable if and only if we can put elements of S in a sequence where you have first position, second position, third position, and so on. Okay. So we can put elements of S in a sequence where we have first position, where we have first position, second position, and so on. Is this clear? Where we have first position, second position, and so on. And so on. Covering every element of S. Covering every element of S. Covering every element of S at least once. Covering every element of S at least once. Okay, covering every element of S at least once. This is the definition number 2. Please tell me, did you understand this definition? See, the definition is simple. S is countable. When can I say S is countable? If you can put the elements in a sequence where you have first position, second position, third position, fourth position, and so on, covering every element of S. Okay, covering every element of S. This is the definition. Please tell me, did you understand? See this. This is the definition. Infinite set is countable. When can I say infinite set is countable? See, every finite set is countable. That you already know. Okay, every finite set is countable. Now, infinite set is countable if and only if it is possible to put them in a sequence. It is possible to list the elements in a sequence indexed by positive integers. Indexed by positive integers means there is a first position, there is a second position, there is a third position, and so on. Is this clear? Let me know. So let's assume there is a set S. Okay, you can have any set S. I don't know what set you have. Okay, so let's assume you have some set S. Now, when can I say S is countable? Please tell me, when can I say S is countable? S is countable if and only if there exists a sequence. S is countable if and only if we can create a sequence. Please understand, we can create a sequence. We can create a sequence, or I can say we can put elements of S in a sequence. We can put elements of S in a sequence. Elements of S in a sequence. Okay, and in a sequence. When I say in a sequence, then remember, this is indexed by positive integers. This is indexed by positive integers. Is this clear? Means there is a first position, there is a second position, there is a third position, indexed by positive integers. Okay, indexed by n. So I can say, so we can put elements of S in a sequence which covers every element of S. Which covers every element of S. Which covers every element of S. Okay, at least once. See, you don't even have to worry about the uniqueness. You don't have to worry about the uniqueness. Just make sure that you cover every element at least one. Just make sure that you cover every element at least once. Okay, you can duplicate also, no problem. You can duplicate also, no problem. But make sure you cover every element of S at least once. Is this definition clear? Let's see some examples. Don't worry, this definition is very, I can say, easy to apply. Okay, but first you read this definition. You can see a set X is countable if and only if there exists a sequence in which every element appears at least once. Just read this. A set is countable if and only if there exists a sequence in which every element of X appears at least once. Okay, is this clear? And remember, this sequence, this is called enumeration. This type of sequence will be called enumeration of X. We will call it, this is, remember, this sequence will be called enumeration of X. Okay, is this clear? And this X will be called enumerable. And this X will be called enumerable. This will be called enumerable. You can call it enumerable, or you can call it countable, or you can call it denumerable. All these are different names for the same thing. Is this clear? All of them, these are different names for the same thing. See, please understand, a set is countable if and only if there is a sequence in which every element of X appears at least once. This type of sequence will be called enumeration. This type of sequence will be called enumeration. And this X will be called enumerable or countable or denumerable. All these are different names for the same thing. Okay, now let's see some questions. Let's solve some questions. Okay, so you understood the definition, right? That countable means you can put them in a sequence where repetitions are allowed. Okay, just make sure every element is covered at least once. every element appears at least once. Okay, just make sure. This sequence will be called enumeration. Enumeration of S. Now let's see some questions. For example, let's prove that set of integers are countable. How to prove it? Set of integers. Let me know. How will you prove that set of integers are countable? This set of integers you already know. This is countable. How will you prove? Just give me a sequence in which every element appears. Every element of Z appears at least once. Every element of Z appears at least once at some finite position. Is this clear? Okay, just give me a sequence in which every element of every element of Z appears at some finite position. So, okay, just last time I'm giving you this note. Just, okay, then we will take examples. This is the note. Remember, if you have a set S, when can I say set S is countable? This point is important. So please focus here. When can I say this set S is countable? If and only if there exists a sequence. This point you already know. Okay, we can create a sequence. If there is a sequence, there is a sequence. Okay, there is a sequence in which every element appears, in which every element of S appears, in which every element of S appears. Every element of S appears at some finite position. At some finite position. At some finite position, maybe first position, second position, third position, and so on. At some finite position. Is this clear? At some finite position. So set S is countable if and only if there exists a sequence, there is a sequence in which every element of S appears at least once at some finite position. Okay, this is the definition. That's it. At some finite position. Now let's apply. So we want to prove that Z is countable. Can you give me a sequence? I want to prove Z is countable. I want to prove Z is countable. Can you give me a sequence? Means first position, second position, third position, and so on. Can you give me a sequence? Will this sequence work? Just, okay, notice I'm giving you. I'm giving you. Will this sequence work? Will this sequence work? Tell me. Will this sequence work? Is this enumeration? Simple question I'm asking. For Z, is this sequence enumeration? Like this is your first position. This is your first position. This is your second position. This is your third position, and so on. This is your fourth position, and so on. So tell me, is this enumeration? Is this enumeration? Why? Why or why not? I'm asking for Z. Is this enumeration? Is this enumeration? Is this enumeration? Tell me. For Z, is this enumeration? See, here you have a first position, right? This is the first position. So there is no problem with the first position. There is no problem with the first position. There is no problem with the second position also. You have second position also. Okay, you have second position also. Then where is the problem? And can I say every element is appearing? 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 Is this enumeration? The answer is no. Because can you notice -1 will never appear? See, this is just an illusion. See, this is just an illusion. -1 will never appear. Please focus. This is just an illusion. Please focus. This is just an illusion. Remember, this is just an illusion. This is just an illusion because -1 will never appear. Tell me, at which position 10? Okay, tell me the position of 10. I am simple. I am asking what the position of 10. Tell me what the position of 10. Let me know. What the position of 10? Position of 10. That is 11th. Okay, there is a finite position, right? Yes or no? That is finite position. Correct? Yes. Agree? Now tell me the position of -1. Now tell me the position of -1. Anyone? Anyone want to give me the position of -1? Anyone want to give me the position of -1? See, this sequence I have given to you. This sequence I have given to you. In this sequence, First position 0, second position 1, third position 2, position of 10, that is 11th position. Now give me the position of -1. None. Yes or no? Give me the position of -1, that is none. -1 will never appear because this itself will go infinity. See, this will never end. See, this will never end, right? Yes or no? Did you notice this? This will never end. So this is just an illusion. -1 will never appear. Is this clear? Here, can you notice? If I give you this, then -1 will never appear. Will never appear. Why -1 will never appear? Because this dot, 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 this will never end. This will never end. Okay. So this is not an enumeration of Z. Is this clear? This is not an enumeration of Z. Please tell me, understood? This is not an enumeration of Z. Is this clear that this is not an enumeration of Z? Let me know. This is the definition. Please read this. Please read this definition. Set S is countable if and only if there is a sequence in which every element appears at some finite position. Every element appears at some finite position. Every element of S should appear at some finite position. So did you understand that this is not an enumeration? Is this clear? This sequence is not an enumeration. Understood? Let me know. So can you give me some other enumeration? Can you give me some other enumeration? Yes. Consider this enumeration. I can put like this: 0, -1, 1, -2, 2, -3, 3, -4, 4. Do you agree with me that every element will appear? Do you agree with me that every element will appear? Just tell me. Do you agree with me that every element will appear? Every element will appear. Yes, this is enumeration. For example, this is your first position. For example, this is your first position. Okay, for example, this is your second position, third position, fourth position. This is your fourth position. Okay, and you can notice here every element will appear. Yes, this is enumeration. Remember, this is enumeration of Z. This is enumeration of Z. Okay, here you can notice every element will appear. For example, tell me what the position. Just tell me a simple question I am asking. What is the position of 10? Let me know. What is the position of 10? Please tell me. What is the position of 10? 2 is at the 5th position. 2 is at the 5th position. Tell me the position of 10. What is the position of 10? Let me know. So that will be 21st. You can notice 21st position. You can see. Okay, you can check it. It will be 21st position. Now tell me the position of minus 15. Tell me the position of -15. Let me know. Tell me the position of -15. That will be 30th. Yes or no? That will be 30th position. So do you agree with me every element will appear? Please tell me, do you agree with me that every element will appear at some finite position? So remember, enumeration of Z. I can give you enumeration of Z. Please notice, I can give you this enumeration of Z. Very simple. This enumeration. -1, 1, -2, 2, -3, 3, -4, 4, and so on. This is enumeration because every element appears. You can easily notice every element of Z appears in this, appears at some finite position. At some finite position. Every element of Z appears at some finite position in this sequence. Okay, is this clear? That's it. So I can say Z is countable. So I can say Z is countable. I can say that Z is countable. Okay, is this clear? Please tell me. Every element of Z appears, remember, every element of Z appears at some finite position in this sequence. In this sequence, every element of Z will appear at some finite position. So I can say this Z is countable. So this is quite easy. This method is actually easy, let me tell you. If you remember, using definition 1, how will you prove this Z is countable? Which is easier? This Z is countable. Tell me, which is easier? Definition 1 or definition 2? Definition 1 or definition 2? See, in the definition 2, you just have to give a sequence. See, please notice, in the definition 2, you just have to give a sequence. You just have to give a sequence. This sequence you can give. This sequence you can give. But in the definition 1, you have to give a bijection. Yes or no? In the definition 1, you have to give a bijection. You have to prove a bijection. You have to prove a bijection from Z to N. Yes or no? You have to give a bijection. Some rule you have to give. For example, what will be Fn? Some rule you have to give. Yes or no? Agree with me? Please tell me. See, in the definition 1, you have to give a bijection. You have to give a bijection, means this type of rule you have to give. You have to give this type of rule. But in the definition 2, you just have to give a sequence. Just give enumeration. In the definition 2, you just have to give enumeration, in which every element appears at some finite position. So let's see the next question. See, prove that set of all finite length binary strings that is countable. Now we need to prove, again, this sigma is your 0, 1. This is sigma. What is sigma star? Sigma star, that is set of all finite length binary strings. This is set of all finite length binary strings. So tell me, how to prove this sigma star is countable? Can you create a enumeration? Can you create enumeration of sigma star? See, very easy to prove. The sigma star is countable. This is very easy to prove. You don't have to give a bijection. You don't have to create a bijection. Sigma star is countable. Just give me enumeration. Anyone? Just give me enumeration. Give me enumeration. Just give me enumeration. Yes, very simple. Just give the enumeration in terms of length. The length of the string. For example, this enumeration you can give in terms of length of the string. Just give me enumeration based on length of the string. For example, this type of enumeration you can give based on length of the string. Yes or no? This type of enumeration you can give me. You can give me this type of enumeration based on the length of the string. Is this clear? So we have enumeration, right? Yes or no? There exists an enumeration, correct? Okay, in this you can notice every element will appear. You can notice every element will appear. Okay, yes, this is enumeration. You can notice every string appears. Every string appears at some finite position. At some finite position, every string will appear. Okay, whatever string you take, that will appear at some finite position. Is this clear? For example, this is your first position. On the first position, you can find epsilon. Okay, for example, you can see this is your fifth position. First, second, third, fourth, fifth. Okay, this is your fifth position. On the fifth position, you can find 0, 1. So every string will appear at some finite position in this. So this is your enumeration. You don't have to give a bijection. Yes or no? You don't have to give a bijection. So because enumeration exists, so what I can say? This is countable because enumeration exists. Because I can enumerate. Enumeration of sigma star exists. Yes or no? So very simple. Enumeration of sigma star exists. So that is the simple idea. Now, using definition 1, what you will do? If you notice, if you want to prove using definition 1, then you have to give this clever bijection. Yes or no? Using definition 1, this type of clever bijection you will have to give from sigma star to integer, from sigma star to natural numbers. This type of clever bijection you have to give. You have to think of this clever bijection. And this is not easy to think. F of W is equal to decimal value of 1W. Decimal value of 1W. Tell me one simple question I'm asking. You let me know. Is this easier to think on your own, or is this easier to think on your own? Tell me. If I give you this question, set of all finite length binary strings is countable, which is easier for you to think in the gate exam. In the gate exam, if some question comes which is easier for you, can you think of this bijection, decimal value of 1w? Is it easier, or is this easier that you just create a enumeration? Enumeration is easy, yes or no? Creating enumeration, that is easy. Just create a sequence, just create a enumeration in which every string appears at some finite position. So this is what I'm saying, that definition 2 is easy to apply. Okay, so this is your definition 2. You can see a set is countable if and only if there is a sequence in which every element appears at least once. In which every element appears at least once. Okay, now we will see definition number 3. So far we have seen definition number 1, definition number 2. At this point of time, what you are thinking, which definition you will apply? If I give you some set and I tell you, prove that it is countable. Given a set, prove that it is countable, which definition you will apply? Most probably you will apply definition number 2. Yes or no? You will create an enumeration. If you can create an enumeration, then I can say, yes, that set is countable. Okay, that set is countable. But tell me one thing. This is a question I'm asking. Using definition 2, can I prove that R is also countable? See, using definition 2, I can prove R is countable. Okay, can I prove R is countable? Can I prove this set of real numbers is countable? Because I can give you enumeration. Because enumeration I can give you. Because this enumeration I can give you. Consider this enumeration. Now tell me, because enumeration I can give you. Enumeration is real line. Is there anyone who can tell me what is the mistake here? Enumeration is the real line. Anyone want to tell me what is the mistake here? Tell me. Using definition 2, can I prove that R is countable because enumeration is this? This is the enumeration. Where is the mistake? Tell me. Where is the mistake? Very simple. Just ask what is the first position? What is the second position? What is the third position? Yes or no? The answer is no. Because just ask what is the first position. Just ask what is first position? What is first position? Okay, just ask what is the first position. What is the second position? What is the third position? Yes or no? Just ask what is the first position, what is the second position, what is the third position. Is this clear? There is no first position, there is no second position, there is no third position. So, did you notice that you have to create sequence in which you have first position, you have second position, you have third position, and so on. And every element should appear. Okay, is this clear? So for example, for the set of real number, can I create this sequence? For example, the first position is 0. Okay, on the second position I can put 0.1. On the third position I can put minus 0.1. Like this, if I create, can I say this is enumeration? Can I say this is enumeration? For set of real number, I give you first position. This first position I give you. I give you second position. Now tell me what is the problem? I give you second position. Now you will be thinking, where is 0.01? Yes or no? Now you will be thinking, where is 0.01? Where is 0.01? Yes or no? Where is 0.00010? Where is that? Where is 0.001? Where is that? Okay, so this is what I'm saying, that you have to make sure every element appears. So this is the definition 2. Please understand. A set is countable if and only there exists a sequence in which every element appears. Every element should appear. You have to make sure that every element appears. Okay. So this is the definition 2. Now we have seen definition 2, definition 1. Now what we will see? Now we will see the easiest definition. The easiest definition, let me tell you. And isko samajh dala to life jinga lala. If you understand this definition, then your life is set. Okay, let me tell you, you can solve every question without taking copy pen using this definition. Isn't that interesting? Every question. Okay, whatever question I give you for countable set, if I give you some set and I ask you, is it countable or not? You can solve every question without taking copy pen using this definition. This is the easiest definition. Just understand this. Isko samajh dala to life jinga lala. So let's see this. First of all, I want to tell you, this definition you will not find in the books. This definition I found in research paper when I was in ISC. Okay, when I was in my MTech from ISC Bangalore, then I found this definition in a research paper. Let me tell you, this definition you will not find in the book. In any book you will not find. In any book you will never find. Okay, so this definition number 3. Now I am discussing definition number 3. Okay, let's discuss definition number 3. This is very easy definition, and I found this definition in a research paper. You can see this is the research paper. You can see a simple approach. The name of the research paper is a simple approach to countability. A simple approach to countability means this definition will make your task very easy. This definition will make your life very easy. This is the research paper. You can see. Okay, research paper by Munibur, Rahman Chowdhury. Okay, so this is the research paper. In this research paper, I found this definition. So one thing I want to tell you, this definition you will not find in the book. In any book you will not find. On the internet also you will not find. You can find this definition either in this research paper or in the Go classes lectures. Okay, you will find this definition you will find only in Go classes lectures other than this research paper. Okay, on the internet also you will not find this definition. If you want to find this definition, then you have to download this research paper. Okay, in this research paper you will find this definition also in the Go classes lectures. So if you are a Go classes student, then this is something you are learning, I can say exclusive. Yes or no? Because I can tell you this definition you will not find on the internet, you will not find on any website, you will not find in the book, in any book. Okay, so this definition you will find either in this research paper or you will find in the Go classes course. Okay, let's see what is this definition. Let's see. So let's see the definition number 3. Are you ready for this definition? Please tell me. Please tell me. Are you ready? See, the definition is very simple. What this definition says that to show S is countable. To show S is countable, all you have to do, see what you need to do. If you want to show that S is countable, all you have to do, this is what you have to do, that this is your set of natural number 1, 2, 3, 4 and so on. This is the set S. Now what you do, just make sure if you want to prove S is countable, what you do, to every natural number you assign a finite set of elements. Okay, finite set of elements you assign means this must be finite. You have to make sure this is finite. This can be very big also. Means to this one, you have to assign finite number of elements. Okay, this can be very big number also. For example, this can be 1 crore. You can assign 1 crore elements, but it should be finite. Is this clear? Similarly, to this 2 also you assign finite number of elements. So finite number of elements you assign to 1, finite number of elements you assign to 2. These two, should they be same? Should they be same? No, they can be different. This can be, for example, this can be 1 crore, this can be 1,000. Okay, but the point is, to this 2 also you assign finite number of elements. To this 3 also you assign finite number of elements. This also must be finite, and that's it. For example, you can assign empty set also. If you don't want to assign anything, you can assign empty set also. Empty set is also finite. Yes or no? Yes or no? Empty set is also finite. To this element, if you don't want to assign any element, if you don't want to assign anything, then that is also fine, because empty set is also finite. That's it. If you can do this and you can cover all the elements of S, if you can cover all the elements of S, okay, like like this. Okay, like this, in the previous image, like this. I am talking about the previous image. Like this, if you can cover every element, if you can cover every element of S, if you can cover every element of S, okay, at least once. If you can cover every element of S at least once, okay, then S is countable. See, this is much easier. Let me tell you, this definition will make your task very easy. Okay. So all you have to do, did you understand what you have to do? Please tell me, did you understand what you have to do? If you want to prove that S is countable, if and only if, this is the definition. This is the definition. S is countable if and only if, what you do? To each n belonging to n, assign a finite subset of S. Okay, assign a finite subset of S such that you cover all the elements. Is this clear? To each natural number, assign a finite subset of S such that you cover every element. Such that every element of S is covered. Every element of S is covered. Okay, that's it. This is the definition. Okay, so just remember this diagram. Please remember this diagram. If you want to prove S is countable, just remember this diagram. Nothing else. S is countable if and only if this is your set of natural number. This is your set S. Did you notice we don't have to give a bijection? Did you notice we don't have to give a bijection? Just give some finite number of elements. Okay, give some finite number of elements to 1. Give some finite number of elements to 1. This is a finite number. Okay, this is a finite subset. Okay, so remember, give some finite number of elements to 2. Give some finite number of elements to 3. You can give empty also. Give some finite number of elements to 4. Okay, so like this. The point is give everyone finite number of elements. Give everyone finite number of elements. You can give empty also. You can give empty also. Give finite number of elements. That's it. To everyone. Okay. Is this clear? To every natural number, you give finite number of elements. But make sure you cover every element of S. Make sure every element of S is covered. Okay. That's it. So very simple. Make sure that every element of S is covered. This is the definition number 3. And this is very easy to apply. So you can see this. S is countable if and only if to each natural number, you can assign a finite number of elements of A covering all the elements of A. Okay. One more thing I want to tell you here. Actually, you can do this also. Okay, no problem. If you have, for example, intersection also is fine. For example, this is your N. This is also fine. This is your N. This is your S. Let's assume to this one, you are giving ABC. Okay, to this one, you are giving, let's assume ABC. And let's assume, to this 2, you are giving C, D, E, F, G. Okay, this is also fine. Is this clear? This is also fine. The only thing is, this must be finite. The only thing is, this must be finite. This must be finite. Okay, means this type of thing is also fine. Basically, this element is covered more than once. That is also fine. This is fine. Remember, okay, this is fine. Is this clear? So very simple. The simple point is that make sure every element of S is covered at least once. Okay, make sure every element of S is covered at least once. This is what you have to make sure. Make sure every element of S is covered at least once. So now let's apply this definition. Okay. Now we will apply this definition on questions. Now let's see, prove that set of integers is countable. Prove that set of integers is countable. This is what we want to prove. Prove that set of integers is countable. You have already seen using definition 1. Yes or no? See, definition 1, you using that you have already seen. In the definition 1, you give a bijection. Yes or no? Here you create a bijection. In the definition 1, you create a bijection. That we have already seen. Definition 2 also we have seen. In this, you create a enumeration. But now let's see the power of definition 3. Now you will feel the power of definition 3. See how definition 3, how easily this definition 3 can prove Z is countable. Okay, please take your copy pen. Please take your copy pen. See how easily this definition 3 can prove that this is countable. So tell me, to 1 what you will assign? To 1 what you will assign? Let me know. Just tell me. To this 1 what you will assign? To this 1 what you will assign? Just assign 0, 1, minus 1. Okay. Or I can just say, see, just assign 1, comma, minus 1. To this 2 what you will assign? Just assign 2, comma, minus 2. To this 3 what you will assign? 3, comma, minus 3. To this 4 what you will assign? 4, comma, minus 4. And so on. Yes or no? Did I cover every element of Z? Did I cover every element of Z? No, 0 is not covered. So you can put 0 also, no problem. Anyway, this is finite, right? Anyway, this is finite. Anyway, this is finite. This is finite. This is finite. And do you guarantee every element of Z is covered now? Now do you guarantee every element of Z is covered? Now do you guarantee every element of Z is covered? Yes. That's it. So Z is countable. So Z is countable. Please tell me, did you like this definition? See, this definition is so simple. To 1 what you will assign, just ask. Just ask to 1 what you will assign. To 2 these, to 3 you will assign these, to 4 you will assign these. Very easy, yes or no? You don't have to do anything. Just apply this definition. So I can say Z is countable. This is your definition number 3. Now let's see. Let's see the power of this definition. See, let's solve this question. Let's solve this question. Set of all finite length binary strings is countable. Set of all finite length binary strings is countable. We have already seen definition 1, definition 2. Yes or no? We have already seen definition 1, definition 2. Now let's see definition 3. Now you will see the power of definition 3. Tell me, how will you do it? Very simple. This is your n. This is your sigma star. Now tell me, what you will do? What you will do? To this 1 what you will assign? Just assign 1 length strings. Just assign 1 length strings. Yes or no? Just assign 1 length strings. Okay, to this 2, assign 2 length strings. Assign 2 length strings. To this 3, assign 3 length strings. Assign 3 length strings. To this 4, what you will assign? Tell me. To this 4, what you will assign? Assign 4 length strings. And so on. And so on. Did we cover every element? Did we cover every element? No, epsilon is not covered. So put it here, no problem. Put it here, no problem. Did you notice? Please notice, please notice. Can you notice this is finite? This is finite. This is also finite. This is also finite. Finite set, finite set, finite set. This is also finite. And can you notice every element is covered? Can you guarantee every element is covered? Can you guarantee every element covered? Yes, every element covered, right? Every element covered. For example, who will cover 100 length string? Who will cover 100 length string? Who will cover 100 length string? 100 will cover. 100 will cover 100 length strings. Yes or no? That's it. So sigma star countable. So sigma star countable. That's it. This is your answer. That sigma star is countable. You can notice that to every element you are assigning. Please notice. For example, how many elements you have assigned to n? You can notice that. Okay, you can notice to any n. To any n. How many elements we assigned? How many elements we assigned? Tell me. To any n, how many elements we assigned? How many elements of sigma star we assigned? Just tell me this point. How many elements we assigned to any n? That is 2 power n. Yes or no? We assigned 2 power n. And this is finite or not? This is finite or not? See, this is finite, right? Yes or no? Agree with me? Do you agree with me that to any n other than 1? Okay, to any n other than 1. N is not equal to 1. To any n other than 1, we are assigning 2 power n. and that is finite. For example, if you have n equal to 100, okay, what you assigned to n equal to 100, what you assigned? You assigned all the 100 length strings. You assigned all the 100 length strings. Okay, you assigned 100 length strings. And how many 100 length strings? That is 2 power 100. And that is finite. That is finite, yes or no? That is finite. So that's it. So you can see this is your definition. Please tell me, did you like this definition? So intuitive and so easy. Let me know. Did you like this definition? Very easily you can prove. And very intuitive also. For example, what you will assign to 3? Just assign all the 3 length strings. What you will assign to 4? Just assign 4 length strings. Very simple, right? Okay, now let's see. Now let's move on. Now let's see that. Prove that every finite set is countable. Prove that every finite set is countable. I want to prove every finite set is countable. So tell me, how will I do that? I want to prove that every finite set is countable. Using definition 1, how will you prove? Using definition 1, how will you prove? Tell me. Using definition 1, how will you prove? Definition 1 contains this condition finite set. Yes or no? If you notice the definition 1 that says that S is countable if it is finite, if and only if S is finite, or bijection. Okay, yes or no? Or S has a bijection with natural numbers. So definition 1 covers. So according to definition 1, this is already included explicitly. Yes or no? So using definition 1, you can prove. Agree with me? Using definition 1, you can prove, because that is already included in the definition 1. In the definition 1, that is already included. Okay, so using definition 1, you can prove that every finite set is countable. How will you prove using definition 2? How will you prove using definition 2? If I give you a finite set, For example, let's assume I give you this finite set. 4, 3, 10, 1, -2, -10. Okay, I give you a finite set. Let's assume this finite set I give you. Now tell me, how will you prove? Using definition 2. Now use definition 2. Use definition 2. So how will you prove using definition 2? Just give a sequence. Yes or no? Using definition 2, create an enumeration. Just make sure you create an enumeration which covers every element of S at least once. Create an enumeration. So yes, I can create an enumeration. For example, will this enumeration work? For example, will this enumeration work that, okay, 10, -2, 1, -10, 4, 3. Will this work? Will this enumeration work? Yes, this enumeration will work. That's it. This enumeration will work. This is the enumeration. You can notice every element is covered. You can notice this is the first position. You can notice this is the first position. Okay. You can notice this is the fourth position. So every element is covered or not? This is the fourth position. Can you notice every element is covered? So yes, this is the enumeration. So create enumeration. Yes, this is the enumeration. So S is countable. So S is countable because there exists an enumeration. Because there exists an enumeration. This enumeration is there. In this enumeration, every element is covered. You have covered every element. Now, using definition 3, how will you prove? Now, something interesting is coming. See, something interesting is coming. You will appreciate definition 3. You will appreciate how easy definition 3 is. I want to prove that this finite set S, you have this finite set S. I want to prove this is countable. Using definition 3, what I will do? Tell me. I want to prove that this set is countable. Using definition 3, what you can do? Tell me. I want to prove this finite set S is there. I want to prove this is countable. Using definition 3, what I will do? Give the entire S to 1. Very good, very good. Give the entire S. Yes or no? Give the entire S to 1. Just give the entire S. Means all the elements you give to 1. To this 1 you can give all the elements. Because this is finite, right? Yes or no? To this 1 you can give all the elements. That's it. That's it. Because this is finite. Because this is finite. So what you will give to 2? What you will give to 2? 5. Yes or no? What you will give to 2? That is 5. And 5 is also finite. 5 is also finite. Yes or no? What you will give to 3? What you will give to 3? You will give 5. That is also finite. Okay, just give 5 to everyone. That's it. This is your definition 3. In the definition 3 is very easy, right? Just give, because this is a finite set, just give all the elements to 1. Just give all the elements to 1. Or what you can do? You can do like this also, if you want. Okay, if you want, you can do this also. To 1 you give A1. To 2 you give A2. Okay, and so on. To n you give an. Okay, and then remaining to n plus 1 you give 5. Is this clear? You can say this is also finite. So that's it. So like this also you can do. Anyway, the point is that finite set is countable. This is the idea. Okay, so finite set is countable. Now let's move on. Now let's see this. Prove that positive rational numbers are countable. Prove that positive rational numbers are countable. In this, again, you will appreciate the definition 3. Again, you will appreciate definition 3, you will appreciate. See, I want to prove set of all positive rational numbers is countable. Set of all positive rational numbers is countable. What are positive rational numbers? Please tell me. What are positive rational numbers? What is the definition of positive rational number? Let me know. Positive rational number, that is q plus. What that? That is any number which I can write as p by q. Yes or no? Or I can say any number which I can write as m by n, such that m comma n, they both are greater than equal to what? Let me know. Positive rational number I'm talking about. I'm talking about positive rational number. So m comma n both are greater than equal to what? Both are greater than equal to 1. Yes or no? Both are greater than equal to 1, because they both must be integers. They both must be integers. M comma n are integers. So this is the definition of positive rational numbers. In this positive rational numbers, you have this type of number. For example, you have 1 by 1, you have 1 by 2, you have 2 by 1, and so on. Okay, so this type of numbers you have in this positive rational number. This is the definition of positive rational number. All the numbers which you can write as m by n, where m comma n are integers, both are greater than equal to 1. This is the definition of positive rational number. Now, how to prove that positive rational numbers are countable? I want to prove that q plus is countable. This q plus, this is countable. Using definition 1, what you need to do? Just tell me. Just tell me, using definition 1, what you will do? I want to prove q plus is countable. Using definition 1, what I will do? I need to give a bijection. Yes or no? Agree with me? I need to give a bijection. Using definition 1, I need to give a bijection. But let me tell you, bijection is too complicated. On the internet, you can find. In the books also, they will not give you. Okay. If you study any book in which they are proving set of positive rational number is countable, you study any standard book, they will not give you the bijection, because bijection is too complicated. This bijection you can find on the math.stack exchange. Okay, here you can find, but this is too complicated. You will never find any standard book which will give you this bijection, because this is too complicated. So can you notice definition 1 is complicated, right? Yes or no? Agree with me? Definition 1, that is complicated. So let me tell you, bijection exists. Yes, bijection exists, but it is too complicated. Books also will not give you. On the math.stack exchange, you can find it, but you can skip. Okay, so using definition 1, of course we can prove. Of course we can prove, remember, because bijection exists, but this is too complicated. Okay, now let's see using definition 2. Using definition 2, what I need to give you? I need to create a sequence, right? Yes or no? I need to create a sequence of rational numbers in which every rational numbers will appear at least once. This type of sequence I need to create. Anyone want to give me a sequence? Anyone want to give me a sequence? Anyone? I want to create a sequence of q plus. How will you give me a sequence of q plus? Tell me. What will be your first number? I want enumeration of q plus. I want enumeration of q plus, which will cover every element. Give me enumeration of q plus, which will cover every element. Yes, okay. The first number you can give me one by one. What will be the second number you will give me? What is the second number you will give me? Tell me. What is the second number you will give me? Let me know. What will be the second number you will give me? Please tell me. Anyone? The first number you will give me one by one, that is fine. What will be the second number you want to give me? It is not easy to give an enumeration like this. Okay, if you are thinking, okay, the second number will be this, the third number will be this, the fourth number will be this, the fifth number will be this, the sixth number will be this, the seventh number will be this. If you are thinking like this, okay, tell me where is the problem? If I give you this type of enumeration, if I give you this type of enumeration, who will never appear? Who will never appear if I give you this type of enumeration? Then who will never appear? For example, 3 by 2. For example, 2 by 3 will never appear. Yes or no? If you do like this, then 2 by 3 will never appear. Agree with me? 2 by 3 will never appear. So like this, randomly you cannot give me enumeration. You can try. Okay, this enumeration is also not easy. Not easy. Not easy. But I can give you, yes, with smart thinking, okay, unless we use smart thinking. Okay. So let's see. See, if you randomly give me this sequence, if you give me, then 2 by 3 will never appear. Okay. So I can say this is not a sequence. This is not an enumeration, right? Yes or no? I can say this is not an enumeration. This is not an enumeration of q plus. Okay. So now let me give you the enumeration. See, the enumeration is like this. What you do? Okay, just notice something smart I'm going to do. Something smart. Okay, this q plus, all the elements you put like this. In this q plus, what you do? You put all the elements like this. Means whenever denominator is 1, you put here. Okay, whenever the denominator is 1, you put here. 2 by 1, 3 by 1, 4 by 1, 5 by 1, 6 by 1. Did you understand? In this row, you put all the, in the first row, you will put when the denominator is 1. In the second row, you put when the denominator is 2. When the denominator is 2. Okay? Is this clear? So far, is this clear? In the third row, you put when the denominator is 3. When the denominator is 3. So far, is this clear? Please tell me. In the fourth row, you put when the denominator is 4. You put when the denominator is 4. Like this, how many rows will be there? Tell me. Like this, how many rows will be there? Like this, how many rows will be there? Please tell me. There will be infinite number of rows. There will be infinite number of rows. Denominator 5, denominator 6, denominator 7, denominator 8. Yes or no? Yes or no? Okay. So this is how you arrange. First you arrange like this. Now see something smart. Now see something smart. What I will do? First I will cover those elements. Okay. Now I am writing a sequence. Okay. Please notice. Now I am going to write a sequence. Now how to write enumeration of q plus? Now how to write enumeration of q plus? Please focus. Please focus. Now how to write enumeration of q plus? I will write like this. First I will put those, okay, whose p plus q is 1. Okay, means first I will put p by q where p plus q is 1. P plus q is 2. I will start because because minimum is this, p plus q will be 2. Then I will put those where p plus q is what? Then I will put those where, tell me. See, first I will put m by n. First I will put m by n. where m plus n is 2. Then I will put m by n, where m plus n is 3. Then I will put m by n, where m plus n is 4. Then I will put m by n, where m plus n is 5. Like this. This is what I'm going to do. Is this clear? Is this clear? Please tell me, did you understand this? Let me know. Now think about it. How will you do this? What is the sequence you will get? Using this idea. You understood the idea? Using this idea, what enumeration, what sequence you will get? Please try. Please try. So did you understand the idea for enumeration of Q plus? Did you understand this idea? The idea, enumeration of Q plus. First, I will put those where the addition m plus n, denominator plus numerator, that is 2. Then I will put those where m plus n is 3. Then those where m plus n is 4, and so on, and so on. Okay, so if you apply this idea, then what is the enumeration you are getting? Using this idea, what enumeration you will get? Using this idea, see, if you use this idea, then this will happen. First, you will cover this. Yes or no? First, this will be covered. First, you will cover this. First, this will be covered. Then who will be covered? Let me know. First, this will be covered. Then who will be covered? Then these two will be covered. Then who will be covered? Then this row will be covered. This diagonal. Then who will be covered? Then this diagonal will be covered. Yes or no? Okay, and so on, and so on. Then this diagonal will be covered. Okay, can you guarantee every Q plus will be covered? Can you guarantee in this, like this if you do, then every element of Q plus will be covered? Yes or no? Like this if you do, then every element of Q plus will be covered. Like this if you do, then every element of Q plus will be covered. Why? Like this if I do, then every element of Q plus will be covered. For example, where will you get this? A simple question I am asking. Where will you get? Where will be this number? For example, 50 divided by 51. Where will be this number? Where will be this number? I can say this number you will find when you do m plus n equal to 101 in that area. Yes or no? In that area you will find. Agree with me? Agree with me? Yes or no? In this area you will find this number. In this area, for example, in this area you will find this number. So did you understand? This is what I'm going to do. Please notice. So what I'm going to do, I can do like this. See, I can do like this. Okay, first I will cover because here you can notice that m plus n is equal to 2. Okay, m plus n, that is equal to 2. Then I will cover where m plus n is equal to 3. Okay, where m plus n is 3. So I will put 1 by 2, 2 by 1. 1 by 2, 2 by 1. Then I will cover where m plus n is equal to 4. Okay, then I will cover where m plus n is equal to 4. That is 1 by 3, 2 by 2, and 3 by 1. Yes or no? Is this clear? Please tell me. Let me know. Okay, so like this. And tell me, is the duplicate? They are same, right? 2 by 2, 1 by 1. They are same, right? Yes or no? 2 by 2, 1 by 1. They are same. You know 2 by 2, that is same as 1 by 1. So if you don't want this duplication, first of all, you tell me, in the enumeration, duplicate is allowed or not? In the definition of enumeration, duplicate is allowed or not? Yes, duplicate is allowed. I told you, enumeration means every element should appear at least once. Every element should appear at least once. So remember, duplication is allowed. So if you want to keep it, you can keep it, or else you can delete it. Okay, remember this point, that in enumeration, duplicate is allowed. This point I told you. in enumeration, duplicates allowed. Duplicates allowed. Repetition is allowed, no problem. Duplicates are allowed. So if you want to keep, you can keep. If you don't want to keep, you can just don't keep. Okay, just don't keep. Yes or no? If you don't want to keep, just don't keep. So like this. Then who will come? Then who will come? M plus n equal to 5 will come. Okay, then m plus n equal to 5 will come. Like 1 by 4, 2 by 3, 3 by 2, 4 by 1. Okay, like this. 1 by 4, 2 by 3, 3 by 2, 4 by 1. Okay, so these people will come. So like this, and so on. Okay, is this clear? So I hope you understood all these points. So remember, if you want to keep the duplicate, that is fine. You can keep the duplicate also, no problem. Okay, like this. So this is the enumeration you are getting. Understood? Please tell me. So this q plus is countable. Is this clear? So this q plus is countable. So remember, because enumeration exists, enumeration of q plus exists, so q plus is countable. So this is the point, that this q plus is countable. The proof, did you understand? Please tell me. Did you understand the proof that q plus is countable? Because there exists an enumeration. We have created enumeration. Enumeration we have created. See, some people, what they will do, they will create this enumeration in a beautiful way. They will go like this. Okay, see, some people, they will go like this. Here they will go like this. Then they will go like this. Then they will go like this. That is also fine. Is this clear? See, some people, they will go in just I can say in a zigzag way. Okay, like this. In a beautiful way, they will go. That is also fine. No problem. What we have done, that is also fine. What we have done, that is also fine. See, some people will go like this. Why they are going like this? So that they can create this type of path. Yes or no? Like, for example, like this. See, this beautiful path. Are you getting my point? See, some people, they will go like this so that they can create up this type of beautiful path. Like this. I hope you understood. Is this clear? What some people will do? Okay, some people will write like this so that they can see this type of beauty. You can notice. Okay, just notice. Like a snack is going on. Like a snack is going on. Okay, so like this. So this is what some people will do. I'm just giving you. This is how some people will write, but that is fine. Okay, that is fine. What we have done, that is also fine. What we have done, like, okay, we have done like this. Yes or no? We have done like this. In one direction we are going. This is also fine. Okay, and if you want this beautification, then this is also fine. Okay, so all these things are fine. Ultimately, I am saying that q plus is countable. So you can see this type of beautiful path. You can see some authors, they will create this type of beautiful path. Okay, like this. So I can say positive rational numbers, they are countable. Is this clear? So far, everything is clear. But now, did you notice, if you want to prove q plus is countable, if you want to prove that q plus is countable, did you notice that definition 1 was too complicated? We did not even see. Yes or no? Definition 1, bijection, was too complicated. Bijection, definition number 1, that means bijection. Bijection was too complicated, right? Too complicated. We did not even see. Correct? Agree with me? This was too complicated. Now, definition 2, that is not easy to think. Yes or no? That is not easy to think. Okay, I can say definition 2, that is not, I can say not naturally, that doesn't come naturally to the mind. Yes or no? Doesn't come naturally to the mind. Agree with me? Doesn't come naturally to the mind. Does it come naturally? This definition 2, this clever thinking, does it come naturally? Please tell me. Please tell me, this clever thinking, does it come naturally? Naturally. No, it does not come naturally, right? Yes or no? So I can say doesn't come naturally. Doesn't come naturally. But now I'm going to use definition 3. It will come natural. It will come naturally to you. And then you will fall in love with definition 3. It will come naturally to you. See, some students, what they think? See, they think that, sir, how will I think like this? See, once I see this solution, I can understand. Okay. Once you see this solution, you can understand. Okay. You can understand also, you can remember also. But now you might be thinking, how will I think like this in the GATE exam? If some new question comes, how will I think like this? This type of clever thinking, how will I think like this? Now I want to tell you, you don't have to think. You can just apply definition 3. That will come naturally to you. Okay, that will come naturally to you. Now let's apply the definition 3. Okay, let's apply the definition 3. Let's prove Q plus is countable using definition 3. All you have to do, to each natural number, assign a finite set of positive rational numbers such that every element of Q plus is covered. Okay, so let's prove that Q plus is definition 3. Using definition 3, can you prove Q plus is countable? This is what you have to prove. Prove Q plus is countable. Just take your copy pen. Prove Q plus is countable using definition 3. That will come naturally. I will not tell you. You will tell me. I will not tell you the answer. You will tell me the answer using definition 3. Using definition 3. Okay, this is your set of natural numbers and this is your Q plus. A simple question I'm asking. A simple question I'm asking. Tell me this, to whom you will map this. Tell me. This you will map to what? Tell me. To whom this you will map? To whom this you will assign? You will assign this to 2. Okay, yes. Many students are saying 2. Yes or no? Tell me, whom you will assign these 2 numbers? These numbers, whom you will assign? You will assign them to 3. Correct or not? Yes or no? For example, what you will assign to 4? What you will assign to 4? What you will assign to 4? To 4, what you will assign? You will assign 1 by 3, 3 by 1, 2 by 2. Duplication is fine. I told you duplication is fine. Yes or no? Duplication is fine. Remember, 1 by 1 is equal to 2 by 2. But duplication is fine. Okay, so please understand this duplication. Please understand this duplication, like this here, this here. See this and this. That is fine. Duplication is fine, no problem. Okay, no problem with duplication. Don't worry about duplication. Duplication is perfectly fine, no problem. Okay, so don't worry about duplication. You just tell me a simple point. So let me know. To 5, what you will assign? How many numbers you will assign? Just tell me. To 5, how many numbers you will assign? Means how many elements you will assign to 5? How many elements you will assign to 5? Tell me. To 5, how many elements you will assign? Let me know. Total 4 elements you will assign. Very good. Total 4 elements you will assign. And that is finite, right? Can I say this is also finite? Can I say this is also finite? Can I say this is also finite? Okay, so that's it. Okay, like this if I do, will I cover every element of Q plus? Can you guarantee every element of Q plus is covered? Can you guarantee every element of Q plus is covered? Can you guarantee every element of Q plus is covered? Yes. For example, who will cover 50 divided by 51? Tell me, who will cover 50 divided by 51? Who will cover 50 divided by 51? Who will cover? Who will cover 50 divided by 51? 101 will cover, right? That's it. Okay, so this is your proof. So Q plus is countable. Yes or no? So Q plus is countable. So Q plus is countable. Because you can easily notice what we have done. Please notice what we have done. To M, because you can notice to N belonging to natural number, what we have assigned? Where N is greater than equal to 2. And to 1, what did we assign? To 1, what did we assign? To this 1, what did we assign to 1? Assign 5. Assign 5. To 1, you can assign 5, no problem. Okay, just assign 5. To this 1, you assign 5. No problem. Okay, so you can see To n equal to 1, what did we assign? To n equal to 1, what did we assign? We assign 5. Okay, that is finite. That is finite. To 2, what did you assign? Tell me. To n equal to 2, what did you assign? You assigned 1 by 1. To n equal to, for example, to n equal to 6, what did you assign? See, to n equal to 6, what did you assign? To n equal to 6. To n equal to 6, you are assigning these where p plus q that is equal to 6. Yes or no? Okay, so tell me, how many such p by q are there? How many such p by q are there? How many? How many? How many? How many such p by q are there? Only 5. Very good, very good. Only 5. Only 5. And that is finite. Okay, that is finite. Is this clear? See, you can check. For example, if I ask you to n equal to 8, what you will assign? To n equal to 8. Then to n equal to 8, you are assigning you are assigning a by b, where a plus b is equal to 8, right? Yes or no? And you can notice a plus b is equal to 8. And you already know a comma b, they are greater than equal to 1. They are greater than equal to 1 and they are integers. They are greater than equal to 1 and they are integers. So what will happen? If a is 1, this will be 7. If a is 2, this will be 6. If a is 3, this will be 5. If a is 4, this will be 4. If a is 5, this will be 3. If a is 6, this will be 2. If this is 7, this will be 1. So how many did you get? Tell me. How many did you get? Only 7. Yes or no? How many did you get? Only 7. Is this clear? So this is the idea. So finally, I can say that you can see q plus is countable. Is this proof clear? Please tell me. So q plus is countable. Did it come naturally to you? This definition 3, this assignment, like to whom this should be assigned? We should assign this to what? We should assign this to what? Is it coming naturally or not? So this is your definition 3. So that's what I'm saying. Definition 3 is very powerful. Very powerful. Now let's see. So tell me, which definition you found easier? I think definition 3. I think definition 3 you found easier. Okay, let's move on. Let's see this question. Prove that all rational numbers are countable using definition 3. Don't even apply definition 2, definition 1. Don't apply. They are too complicated. Prove that all rational numbers are countable using definition 3. It is cakewalk for you. Take a copy pen. Take a copy pen. Just take a copy pen. Tell me what you will assign to 1. Just tell me what you will assign to 1. What you will assign to 1, let me know. To 1 you can assign, for example, 0 you can assign, right? See, to 1 you can assign 0. Okay. Now, to 2 what you will assign? To 2 what you will assign, tell me. Now you can assign 1 by 1 also and minus 1 by 1 also. Yes or no? To 3 what you will assign? To 3 what you will assign, tell me. To this 3 what you will assign, let me know. See, now you will assign, for example, you will assign 1 by 2, 2 by 1, minus 1 by 2, minus 2 by 1. Yes or no? Okay. Yes or no? To 4 what you will assign, let me know. To 4 what you will assign? To 4 what you will assign? How many? Just tell me how many. Just tell me how many. To 4 what you will assign? How many? I am asking how many you will assign. To this 4, how many you will assign? Very good, 6. Very good, very good, very good. Very good, 6. Okay. Is this clear? So 6 you will assign. So you can note this is also finite. 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 Hence Q is countable. Hence Q is countable. I hope you loved the definition 3. Can you see how easy it is? This definition 3, how easy it is. Okay. Now I want to tell you something. On the internet, if you find this proof, you will not even find it. You will not even find it. On internet, if you want to find this proof, set of all rational numbers is countable, you will find on the Math Stack Exchange, on that website. math.stackexchange. On that website you will find, but that you just go through that. That is too complicated. That proof is too complicated. But using definition 3, I can simply say that you can easily do. Yes or no? That you can easily do. Agree? Please tell me. Did you understand? Please tell me. Let me know. Yes or no? Is this clear? Please tell me. So very simple. This is the simple idea. So like this you can prove. Tell me one thing. Okay, so this Q is countable. Remember in this, if you notice one thing, how many we are assigning to n? Okay, if you have, for example, if you have n equal to, let's assume 10. How many did you assign? How many? How many assignments? Tell me. To n equal to 10, how many assignments? Very good. That is 18. Okay, 8 positive, 9 positive, 9 negative. Yes or no? 9 positive and 9 negative. Correct. So that will be 18. That will be 18. Very good. So to n, if you take n, okay. So to n, what you are assigning? How many? To any n. How many you are assigning? Tell me. You are assigning 2 multiplied by n minus 1. Yes or no? Or I can say n minus 1 plus n minus 1. N minus 1 plus n minus 1. These n minus 1 for positive. These n minus 1 for positive. And these n minus 1 for negative. Is this clear? Okay. This n is greater than equal to 2. Please tell me, understood or not? And you can notice, to this 1 you can assign 0. This 0 you can assign to 1. Okay, this 0. To this, if you have this n equal to 1. To n equal to 1, what you are assigning? Assign 0. Assign 0. To n equal to 1, you assign this 0. So that's it. So finally, I can say Q is countable. Set of rational numbers is countable. So this is the proof. You can see in this research paper, this proof is given. Simple proof. Let's move on. Okay, let's prove this. Prove that n cross n is countable. We want to prove n cross n is countable. First of all, what is n cross n? Tell me. Tell me what is n cross n. That means z plus cross z plus. This is cross product. This is your cross product. This is your Cartesian product. This is the Cartesian product. Or I can say cross product. So this is your cross product. So tell me, what you have in n cross n? In n cross n, what you have? Let me know. In z cross, z plus cross z cross. So in this you have ordered pairs, right? This type of ordered pairs you have. This type of ordered pairs you have. So this is what you have. Agree with me? This is your n cross n. This is element in n cross n. This is element of n cross n. Okay. So like this. In this n cross n, you have ordered pairs. All these are ordered pairs. This is element of n cross n. Remember, this is an element. This is element. Okay. So now what we need to prove? We need to prove that this n cross n, this is countable. This n cross n, this is countable. Using definition 2, how will you prove? I want to prove this is countable. Set of ordered pairs from n cross n. Using definition 2, can you give me enumeration? Can you give me enumeration? Anyone? Can you give me enumeration? Yes, very good. Snake type of structure. Very good, very good. Okay, so first you arrange like this. See this n cross n. First you arrange like this. Okay, when the first element is 1, you put here. See, when the first element is 1, you put here. In this row, you put when the first element is 1. In this row, you put when the first element is 2. Is this clear? When the first element is 2. And then you put when the first element is 3. When the first element is 3. When the first element is 3. Then you put when the first element is 4. and then you put when the first element is 5 and so on. Yes or no? So how many rows will be there? Please tell me. How many rows will be there? Infinite. Yes or no? How many rows will be there? Infinite number of rows. Okay. And you can notice like this. So this is how you arrange. Now tell me what you will do. Let me know what you will do. Very simple. Just go like a snake. See, just go like a snake. Yes or no? Just go like a snake. Like this. Just go like a snake. Okay. Like this. Just go like a snake. Then what you will do? Just go like a snake, nothing else. Just go like a snake, nothing else. That's it. That's it. Just go like a snake, nothing else. Okay, like go like this. Okay. Like this you go. Is this clear? See what is happening here. Okay. And so on. Is this clear? Please tell me. So like this you can create the enumeration. So what enumeration you will get? Let me know. What is the enumeration you are getting? So the enumeration of n cross n. What is that? So the enumeration of n cross n. What enumeration you are getting? Let me know. You are getting this enumeration. First you are putting 1 by 1. Okay. Then you are putting what? Then you are putting 1 by 1. Then you are putting what? Tell me. In this snake structure. In this snake structure. In this snake. First you are putting 1 by 1. Then you are putting 2 by 1. Then you are putting 1 by 2. Then you are putting what? Then you are putting what? Then you can see 1, 3, 1, 3, 2, 2, 3, 1. 1, 3, 2, 2, 3, 1. Then what you are putting? Then what you are putting? Then you are putting 4, 1, 3, 2. Then you are putting 4, 1, 3, 2, and so on. And so on. So that's it. Yes or no? So this is the enumeration. So because enumeration exists, so I can say n cross n is countable. N cross n, that is countable. This snake type of enumeration is there. Okay, yes or no? Like this you can enumerate. Like this you can enumerate. Clear? Now tell me one thing. Can you prove it using definition number 3? Using definition number 3, how will you prove it? N cross n is countable using definition number 3. It will come very naturally to you. It will come very naturally. So tell me, using definition number 3, I want to prove n cross n. Tell me one thing, simple question I'm asking. Whom will you assign this 2, 1? To which number you will assign 2, 1? 2, 1, 1, 2. These things you will assign to what? These things you will assign to 3. Very good. Very good, very good, very good. Okay. To whom you will assign this number? To whom you will assign this number? This you will assign to 2. This you will assign to 2. So to 1 what you will assign? To 1 what you will assign? You assign 5. You assign 5. To 1 you assign 5, right? Yes or no? Okay, just assign 5. Means don't assign anything. To this 1 you don't assign anything. To 4, how many elements you will assign? To 4, how many elements you will assign? Tell me. How many elements you will assign? To 4. Very good. Finite number of elements. How many? Finite number of elements. How many? 3 elements you will assign. Yes or no? 3 elements. Okay, you will assign 3 elements. You can check. Okay, to 4 you will assign, for example, 1, 3, 3, 1, and 2, 2. Okay, like this and so on. 200, how many elements you will assign? 200, how many elements you will assign? Just tell me. How many elements you will assign? How many? Let me know. 99 elements you will assign. Right, very good, very good. Very good. 99 elements you will assign. Okay, and so on. So tell me, can I guarantee every element of n cross n is covered? Can I guarantee every element of n cross n is covered? Can I guarantee every element of n cross n is covered? Yes. Okay, see, notice. If you have n equal to 1, what you are assigning? What you are assigning? You are assigning 5. Okay, you are assigning 5. That is finite. That is finite. Okay. Now, if you have n greater than equal to 2, if you have n greater than equal to 2, then how many you are assigning? Just tell me. If you have n greater than equal to 2, how many assignments? How many assignments to n, if n is greater than or equal to 2? How many assignments? That is equal to n minus 1. Is this finite? For any natural number, this is finite, right? For any natural number, this is finite. Agree? Yes or no? For any natural number, this is finite. These many ordered pairs, n minus 1 ordered pairs you are assigning. You are assigning these many ordered pairs, and that is finite. So that's it. And tell me one thing, is every element of n cross n covered? Is every element of n cross n covered? Is every element of n cross n covered? Did you cover every element? The answer is yes. We have covered every element, right? Okay. So because whatever element you take, see, if I give you this element of n cross n, if I give you this element of n cross n, to whom did you assign it? To whom did you assign it? Assign to. To whom did you assign it? Assign to a plus b. Assign to a plus b. Okay, very good. So this is your proof. How easy it is? Please tell me. Yes or no? So you can see this is the question. Prove that z plus cross z plus is countable. Using definition 3, this is so easy. I hope you loved the definition. Definition number 3. Now, please tell this question also. Try this question also. Can I give you this question as a homework? This question is saying whatever alphabet you take, sigma star is countable. See, this question is saying whatever alphabet you take, whatever alphabet you take, sigma star is countable. Okay, sigma star is countable. Tell me, how will you prove it? Using definition 3, that is your favorite definition now. Your favorite definition now. Whatever sigma you have, you can have any sigma. You can have any sigma. Then prove that sigma star is countable. Prove that sigma star is countable. Okay, remember sigma star has what this is the set of, this is the set of all finite length strings, right? This is the set of all finite length strings over sigma. Over sigma. Okay, this is the set of all finite length strings over sigma. Now prove that this is countable. Whatever sigma you have. For example, your sigma can be anything. For example, your sigma can be AB to Z. This is also fine. Okay, then also sigma star is countable. Then also sigma star is countable. Whatever sigma you take, of course, sigma must be finite, right? By definition, sigma is finite, non-empty. By definition, sigma is a finite set. Okay, so you can see. So whatever sigma you take, sigma star is countable. How will you prove it? Tell me. Very simple. Just tell me using definition 3. Using definition 3, this is your sigma star. Okay, so what you will do? How will you assign? Very good. Assign by length. Very good. Very good. Assign by length. Very good. Okay, so tell me, to this one, what you will assign? To this one, what you will assign? You will assign one length strings. Also assign epsilon. Also, no problem. Yes or no? Okay, assign one length strings. Epsilon also you assign. Assign epsilon also, and also assign one length strings. So tell me, how many elements you are assigning? How many? How many did you assign? Just tell me, how many did you assign? To this one, how many did you assign? See, assign epsilon also. Put epsilon also, no problem. Put this epsilon also, no problem. Okay, just put it. So how many did you assign? You assign cardinality of sigma plus 1. Very good. Is this finite? Is this finite? Yes, this is finite, right? This is finite. Okay, very good. This is finite. Okay, because sigma is a finite set. Because sigma is a finite set. So cardinality of sigma, that is finite. Okay, cardinality of sigma, that is finite. So you can see sigma is a finite set. Now tell me, to 2, what you will assign? To this 2, what you will assign? Just tell me. You will assign all 2 length strings. All 2 length strings you will assign. How many are there? Tell me, how many? All 2 length strings you will assign. But how many are there? That is cardinality of sigma multiplied by cardinality of sigma. That is cardinality of sigma whole square. Yes or no? Cardinality of sigma whole square. To this n, what you will assign? See, to this if I have this n, if I have this n, to this n you will assign all the n length strings. You will assign all n length strings. Just assign all n length strings to this. Okay, is this clear? So how many? Tell me how many? Tell me how many? That is cardinality of sigma power n. Very good. Yes or no? And so on. So that's it. So this is your proof. Did we cover every element of sigma star? Did we cover every string? Did we cover every string? Yes. Yes, we are covering every string. So that's it. This is your proof. So remember what we have done. To n equal to 1, what did you assign? What did you assign? To n equal to 1, what did you assign? You are assigning all the one length strings and epsilon. Epsilon, comma, all one length strings. All one length strings. Okay. Now, if you notice, if you take any n greater than equal to 2, if you take any n greater than equal to 2, what you do? You assign all n length strings. You assign all n length strings. How many? Assign all n length strings. How many are there? How many are there? Okay. I want n length strings. How many are there? That is sigma cardinality power n. Okay. Because how many n length strings are there? Just notice. If your sigma is something, your sigma can be, let's assume you have sigma, then how many n length strings you can create? Notice how many n length strings you can create. I want to create n length strings. I want to create 1, 2, 3, and so on n. So tell me, for every position, how many choices you have? Here you can put any symbol from sigma. Yes or no? Here you can put any symbol from sigma. So these many choices I have. Here also these many choices I have. Okay, here also these many choices I have. So finally I can say how many? That will be cardinality of sigma power n. This will be the answer. Correct. So I can say this is finite number. Okay, so that's it. So finally, this is the idea. Yes or no? Agree with me? Okay. So easy. Now let's move on. Now let's see this question. This is our last question. Please try this also. This is our final question. We are practicing definition number 3. We are doing the practice of definition number 3. Now you are expert of definition number 3. Now you are expert of definition number 3. So tell me, prove that set of all finite subsets of n. Prove that set of all finite subsets of n is countable. First you understand this. First you understand this. What the question is asking. See what the question is asking. The question is asking, in here you have finite subset. Remember, you have finite subset where A is a finite subset of n. Please understand, where A is finite subset of n. So which type of elements you have in this base set? What you have here? What you have here? For example, can I say phi you have? Can I say you have phi? Yes, phi is a finite subset of n. Finite subset of n. Finite subset of n. Do you have n here? Do you have n here? Do you have n here? No, you don't have n here. You don't have n. Finite subset of n. You don't have n. N is any set of natural number. That is infinite. N is set of natural number. That is infinite. Your n, that is set of natural numbers. This is infinite. Is this clear? Did you understand the question? Please understand the question. A is finite subset of n. A is finite subset of n. For example, do you have this? Yes. Do you have this? Yes. Do you have this? Yes. For example, do you have this element? Yes, very good. Do you have set of prime numbers? Do you have set of prime numbers? Do you have set of prime numbers? Set of prime numbers. No, that is not finite. Yes or no? You don't have set of prime numbers, right? Okay, so basically you have finite subset. That point is simple. For example, you can have this. For example, this is also there, and so on. Did you understand the question? Let me know. Did you understand the question? Remember, this is your set. In this set, you have subsets, finite subset of n. A is finite subset of n. Is this clear? A is finite subset of n. Now, we want to prove that this is countable. Prove it is countable. Prove that S is countable. This is what we have to prove. We have to prove S is countable. Okay, using definition 3. Just try definition 3. Just try definition 3. So tell me, using definition 3, what assignment you will do? This is your n. 1, 2, 3, 4, and so on. To this one, what you will assign? This is your set S. To this one, what you will assign? Tell me. To this one, what you will assign? Let me know. Will you assign all one-side subsets? Will you do this? Will you do this? All one-side subset. Will you do this? Will you do this? All one-side subset. Will you do this? All two-side subset. Tell me, will you do this? All one-side subset, all two-side subset, all three-side subset? No, 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 no. This is infinite. How many one-side subsets are there? How many one-side subsets are there? Tell me a simple question. You have this n, and you already know. This is your n. How many one-side subsets? How many one-side subsets you can create? Tell me, how many one-side subsets you can create? That is infinity. Yes or no? Infinite. For example, you can create this. For example, you can create this. For example, you can create this, and so on. Is this clear? Please let me know. So this idea will not work. Yes or no? This is also infinite. Will this idea work? Will this idea work? Tell me. If you are thinking that I will do this, will this idea work? This idea will not work. So what to do? So the previous idea does not work. So previous idea doesn't work. Idea doesn't work. Okay. So tell me, previous idea doesn't work. Now what? The previous idea will not work. Give me some other idea. Using definition 3. You can do that. Using definition 3, give me some other idea such that you will get only finite number of assignments. Give me some other idea. Give me some other idea such that you will get finite number of assignments. Very good, Satyam. Very good. Sum of subset. Excellent, excellent, excellent. Just assign sum of subset. Summation wise. Go summation wise. This is the idea. Assign summation wise. Assign summation of elements. Is this clear? For example, to this one, what you will assign? To this one, what you will assign? Only this is what you can assign. Yes or no? Only this is what you can assign to this one. To this two, how many you will assign? Let me know. To this two, how many you will assign? See, you will assign what? To this two, how many you will assign? This is the only choice, right? Yes or no? This is the only choice. Agree? To this 3, how many you will assign? Let me know. You can assign this. You can assign this. These you can assign, right? Agree? Please tell me. Do you agree with me? To this 4, how many you will assign? See, you can assign 2, 2. You can assign 1, 3. You can assign 4 also. You can assign 4 also. So you can notice, you can assign 4. You can assign 1, 3. You can assign 2, 2. What else? What else? What else? You can assign. Is there something else? I think that's it. I think that's it, right? Is there something else? No. Okay, for example, can I do this? Can I do this 1, 1, 2? 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 No, this is, see, this is 1 here. This is just 1, 2. Please understand. Why are you not understanding? Remember these two set. This 1, 1, 2. This is same as 1, 2. So here the summation is what? If I ask you here the summation is what? Tell me. Just tell me here the summation is what? Here the summation is 3 only. Is this clear? Here the summation is 3 only because they are same. Because they are same. Is this clear? For example, this set, look at this set. This is a set, remember. In a set, duplicates are allowed or not? Duplicates are not allowed. This is same as this. Is this clear? Please tell me. In a set, duplicates are not allowed. Set is a collection of distinct unordered elements. Is this clear? Set is collection of distinct unordered elements. For example, this 1, 2, this is same as 2, 1. Is this clear? For example, tell me simple question I'm asking. What is the summation here? What is the summation here? That is 2 only. Because this set is exactly same as this set. They are exactly same. Okay, so let's come to this point. So you can see to 1 you will assign this, to 2 you will assign this. This 2, 2 is also wrong. Yes or no? This 2, 2 is wrong. Correct? This 2, 2, this is wrong. Okay, so to this 4, what you will assign? You can assign 1, 3, you can assign. Notice, you can assign 1, 3, you can assign 4. Okay, you cannot assign this also. Is there anything else we can assign to 4? Is there anything else we can assign to 4? Please tell me. Do you have anything else which you can assign to 4? No, nothing else, right? Okay, that's it. So, do you agree that everyone will get a finite number of elements? Yes or no? So, assign summation wise, summation of elements. Is this clear? Please tell me. Let me know. So, you can notice, just do this. Just assign summation of elements. Means, if you have this set, for example, let's assume this subset you have 2, 3, 10, 99. Okay, this you will assign to whom? This you will assign to whom? Tell me. This you will assign to whom? This will be gone to whom? This will be gone to, just do the addition. Just to do the addition. This will go to 114. Very good. This will go to 114. Okay, it will go to 114. Clear? Okay, so this is the point. Oh, and can you guarantee this will be finite? Like how many you will assign to? How many you will assign to this? For example, you can assign this to 114. You can assign something else also, but that will be basically that will be finite. Yes or no? So this is the idea. Is this clear? Hence I can say S is countable. Hence S is countable. So did you love the definition 3 or not? Please tell me. So remember what was your S? Please understand. This S is a finite. This is set of finite subsets of N. Finite subsets of N. Okay, finite subsets of N. And this is countable. Finite subsets of N. This is your definition number 3. That's it. So we have seen everything. This definition number 3, we have seen everything we have seen. So please tell me, what do you feel about this definition? You have seen definition 1, 2, 3. Definition 1, that is a formal definition. In that we create a bijection. Definition 2, that is enumeration. We create enumeration. Definition 3, that is so simple. Yes or no? And definition 3 comes to your mind naturally. See, whenever you apply the definition 3, it will come to your mind very naturally. It will come. You don't need a smart idea. Like, okay, very smart, very clever idea. No, this will come very naturally. this definition 3, it will come very naturally to your mind. So how do you feel about this definition? Please tell me. These are the options, option 1, 2. So please comment. Okay. So did you like this definition, definition 3? Please tell me. Has it become your favorite? The definition 3 of countable set. Okay. So please comment. Okay. Please comment this video. I will upload on the Go Classes YouTube channel, and please share your opinion in the comments. Please give me a feedback in the comments. Okay. So this definition 3 is very simple, very intuitive. You can apply this definition and you can solve all the questions. You can prove whatever countable set I give you and I ask you, prove it. I give you some countable set and I tell you, prove it. Then you can apply the definition 3 and you can easily see. Okay. So please share your opinion in the comments. Please do comment. Okay. So how do you feel about it? Liked it, loved it? Let me know. In the comments, let me know. Okay. So thank you, everyone. Now, in the next lecture, we will study Cantor's theorem. This Cantor's theorem, this is very important. This we will study. We also have to study some theorems of countable set, like union of countable set, cross product of countable set, intersection of countable set, subset of countable set. So these theorems also we need to study. Okay, and some practice we will do. So this is what we will do in the next lecture. Thank you, everyone.